In this video, we're going to talk about putting numbers into perspective, which means we're going to talk about really large numbers and really small numbers. And when you're working with large and small numbers, it's much easier to write them in a format known as scientific notation. And when we write something in scientific notation, it's written as a number between 1 and 10, and then it's multiplied by a power of 10. So for example, I might have something like 4.2 times 10 to the 7th. So it's always going to be a number between 1 and 10 on the left, and then you multiply by a power of 10. Now, if that power, in this case, in the example that I'm using here, is 7, if that power is a positive number, then it's going to be a large number, meaning you move the decimal place to the right, which would make it bigger. And then if the power is a negative number, then you would move your decimal place to the left, which would make it a small number. So in the first example we're going to talk about, it says rewrite each of the following statements using scientific notation. So in part A, it says the total spending in the new federal budget is $3 trillion, $900 billion. So we are going to write this in scientific notation. Now I want the first number out in front, when I write this as scientific notation, to be a number between 1 and 10. So I'm going to rewrite it as 3.9. 3.9. I don't want to write it as 39 because that's not between 1 and 10. And I don't want to write it as 0.39 because that would be less than 1. It has to be between 1 and 10. So I'm going to rewrite the 3 trillion number as 3.9 times 10 to the power of, and then we've got to figure out what the exponent is. Now to figure out what the exponent is, so that these two numbers are the same and just written in two different ways, I'm going to look to see how many times I move my decimal place over to get to 3.9. So if I count, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm moving my decimal place 12 places. So my exponent is going to be 12. So $3,900 billion is going to be written as 3.9 times 10 to the 12 dollars. And these are exactly the same number, just like if I write 0.5 and 1/2, they mean the same exact thing, they're just written in a different way. Part B says the diameter of a hydrogen nucleus is, and then it gives us this really, really small number. Now I want to write my first number between 1 and 10. So I'm going to write it as 1.0 times, and then I got to figure out what my exponent is going to be for my power of 10, and that just tells me how many decimal places I move. So if I count all my zeros and I move my decimal place over 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15. That's 15. However, since this is a really small number, and when I multiply this out, I want to move my decimal place to the left, I want to make sure that that's a negative 15 to indicate that that's a really small number. And then this is, of course, in meters. Now, to do scientific notation calculations on the calculator, what we're going to do is use a button that tells us that we're working with powers of 10, and that button is right above the comma right here, and it says double E. When you hit that button, it actually comes up as a single E, but it's noted as a double E, as not to get it confused with the letter E if you're typing out letters. Okay, so to access the double E here above your comma, you have to hit the second button first, and then the comma button to access the double E. So if I want to take 3 times 10 to the 4th and divide by 2.5 times 10 to the negative 2, what I'm going to do is I'm going to hit the button 3, and then I'm going to use the double E button to show that I'm working with powers of 10. So then I'm going to hit the second button and then the comma button. That's going to give me my single E, even though the button says double E. And then what I'm going to do is put down what my exponent is. So my exponent is 4. It's 3 times 10 to the 4th. So that E is replacing the times 10. And you're just putting in the exponent. Now I want to divide by 2.5 times 10 to the negative 2. So then I'm going to hit the second button and the comma button to get to my E button. And then I'm going to hit the negative button and the 2. So that's 3 times 10 to the 4th divided by 2.5 times 10 to the negative 2. When I hit enter, this is my answer. I get 1, 2, 0, 0, 0, 0, 0. Now, if I want to rewrite that in scientific notation, that would be 1.2, because I want my first number out here to be between 1 and 10, times 10 to the power of. Now, since this is a really big number, my exponent is going to be positive, and I've got to figure out how many places I move my decimal to get the 1.2. So right now, my decimal's here, and I'm going to move it over 1, 2, 3, 4, 5, 6. So that's times 10 to the 6th. You can put your calculator in scientific notation mode if you would like by hitting the mode button and then scrolling over to scientific and hit enter. So now instead of being in normal mode, you're in scientific notation mode. And when I go back to the home screen, if I tell the calculator to do 3E4 divided by 2.5 e to the power of negative 2, and I hit enter, it's going to give me my answer in scientific notation. So my scientific notation, so these are the same answer, they're just written 2 different ways. So my answer in scientific notation is 1.2, and then the e represents the times 10, and then 6 is my exponent. Now, my calculator will stay in scientific mode until I go back and change it. If you're familiar with your exponent rules, when you write numbers in scientific notation, it makes it easy to approximate answers without a calculator. So, for example here, it says we're going to approximate the answer of 5,795 times 326. The actual answer, if you do that on your calculator, is 1,889,170. But we can approximate it by saying the 5,795 is close to 6,000 times, and the 326 is close to 300. And then if we write that in scientific notation, that's 6.0 times 10 to the power of 3, right, because I moved it 1, 2, 3 places. And then that's times 3 times 10 to the second power because I moved it 2 places. Now, if you remember your exponent rules, when you multiply and your bases are the same, you add your exponents. So I'm going to multiply my numbers together to get 6 times 3, which is 18. And then I'm going to multiply my powers of 10 together. So I have 10 to the 3rd times 10 squared. So that's going to give me 10 to the 5th using my exponent rule that I add my exponent when I multiply like bases. And then this isn't technically in scientific notation quite yet because that number isn't between 1 and 10. That means I have to move my decimal place 1 more place so that it is a number between 1 and 10. So I'm going to write it as 1.8 times 10 to the 6th. Now, if I multiply that out and write it in normal mode without the scientific, if I just write it in standard form, that's 1/8 1, 2, 3, 4, 5 zeros. Because I take this decimal place and I move it over 1, 2, 3, 4, 5, 6 places. So we just approximated 5,795 times 326 by rounding, putting it in terms of scientific notation. And then, so our approximation is 1,800,000. And the exact answer is 1,889,170. So if you're comfortable with your exponent rules, you can quickly approximate just by using your exponent rules with powers of 10. Okay, now that we reviewed scientific notation, we're ready to go and start talking about putting numbers into perspective. And with problem solving, there's no single recipe for putting things into perspective, but there are a few simple techniques that can be helpful. We're going to talk about 3 techniques. We're going to talk about estimations, comparison, and scaling to be able to put numbers into perspective. That doesn't mean these are the only 3 options, but these are the ones that we're going to talk about in this video. So to start off, we're going to talk about how high is 1,000 feet. And for most people, it's hard to visualize what 1,000 feet is because it's a really big number. At least I know it is hard for me to visualize it. So it's good sometimes to put things into perspective by estimating it and comparing it to things that you already are comfortable with or familiar with. So what I'm going to do is I'm going to compare it to a building that is 1,000 feet so I can picture what that would look like. Now, when I think of a story or a floor of a building, I think that that's about 10 feet. So 1 floor of a building is approximately 10 feet. So if I take 1,000 feet and divide it by 10 feet, I'm going to get 100. So if I think of each story as being 10 feet, when I imagine a building that's 1,000 feet, I can imagine that it's about 100 floors. So that's putting it into perspective for me, and I can now imagine how tall this building is. Some estimates are very useful even if they only get us within a broad range of an exact value. For example, you can infer a lot about the character of a town or a city by knowing whether its population is in the 10,000s or in the millions. Estimates that can give only a broad range of values, such as in the millions or in the hundreds, that's called an order of magnitude. So that's a method we're going to use to make estimations about very large numbers. Okay. So the first example that we're going to talk about is we're going to make an order of magnitude estimate of a total annual spending on ice cream in the United States. And again, this isn't going to be exact. This is going to give us a broad range for an approximation. Let's start off by listing. This is going to be the total spending per year on ice cream. And this is going to be in the United States, the entire United States. So first of all, we're going to figure out how many servings per person per year. Then we're going to figure out the price per serving. And then we're going to multiply it by the number of people in the US, because then I can get rid of servings and then people, and I'll be left with price per year, which is what we're looking for. It's asking us to make an order of magnitude to estimate the total annual spending, which is per year, of everybody in the United States. So if, for me, because I'm going to use myself as an example, I would say maybe I have ice cream twice a month. And so since there's 12 months in the year, that would be about 24 times a year. So 24 servings per person per year. This is just an estimate because it might be different for other people. Remember, this is just going to give us a very broad range estimate. And I would estimate that it's probably about $2 for ice cream. If you go to the ice cream stand, it's probably about $2 for an ice cream. And that's $2 per serving. And when I looked it up, I found that there's 300 million people in the US, approximately. So when I multiply this all out on the calculator, I'm going to get 24 servings times $2 a serving times 300 million people. You're going to get 1.4 times 10 to the power of 10, and that's in dollars, and that's per year. And that is because I got rid of servings, and then this is the number of people. So I'm left with dollars per year. Now, when you put this in on the calculator, remember that millions would look like this. So if I have 300 million people, it would be 300 and then 6 zeros. That would be 300 million when you go to put that in on the calculator. Or you can go ahead and use scientific notation and put it in as 3 times 10 to the 8th. Because I've got 1, 2, 3, 4, 5, 6, 7, 8 spaces that I would have to move over, decimal places. Okay, now it says make an order of magnitude estimate of the number of hours you spend in a shower or bath per year. So for me personally, I would say every time I take a bath or a shower, I'm probably in the shower for about 15 minutes. So I would say 15 minutes per day. But we're trying to figure out how many hours per year. So I want to change minutes to hours, and I want to change days to years. So to get rid of the minutes, to change it to hours, I'm going to say there's 60 minutes in 1 hour. So that put it in hours because I can cross off my minutes. Now I want to change days into years. So there are 365 days in 1 year. So I can get rid of the days now. And I'm left with hours per year. So I'm going to put that in the calculator. And I'm going to take 15 over 1 times 1 over 60 times 365 over 1, and I'm going to get 91.25 hours per year. Okay, next we're going to talk about perspective through comparisons. And comparisons are really helpful when we're dealing with units that we're not really familiar with, such as energy and joules. So I have a table here with information about U.S. and world energy consumption. And we're going to use that to complete the next 2 examples, part A and B. So in part A, it says how many liters of oil are required to supply the electrical energy needs of an average home for a month. So we want to look up on the table the energy needs for an average home for a month, And then we want to figure out how many liters of oil that's going to take. So if we scroll up here and look at the table, I have energy released by burning 1 liter of oil here. That's this energy, 1.2 times 10 to the 7th joules. And then we also have electrical energy used in an average home daily, and we can use that as well. There isn't anything on the table here that talks about the energy used in an average home monthly, but we can use the one for daily and just change it into per month using unit analysis. Okay, so we're going to first start off by taking the 5 times 10 to the 7th joules per day, and we're going to change that to per month. Now let's assume that there are 30 days in a month. I know there's sometimes 31 and then the special case of February, but just on average, just so that we can put something down, we're going to say that there's 30 days in 1 month. Okay, so by doing that, I got rid of the days and I turned it into energy in joules per month. Okay, now we're going to figure out how many liters of oil that's going to take. Now, according to the table, it says it's going to take 1 liter of oil to burn 1.2 times 10 to the 7th joules. Since I want to cancel out joules, so I'm left with liters of oil, I'm going to put the joules on the bottom. So I have 1.2 times 10 to the 7th joules, and that will give me 1 liter of oil. So now I can cross off the joules, and I'm left with liters of oil per month. So I'm going to go ahead and put that in on the calculator, and I'm going to put 5 times 10 to the 7th over 1 times 30 over 1 times 1 over 1.2 times 10 to the 7th. We're going to get 125 liters of oil. Now in part B it says if you could generate energy by fusing hydrogen and water, how much water would it take to supply all the energy needs of the world in 1 year? So we want to compare the amount of water needed to use or to generate the energy needed by the world in 1 year. So if we scroll up, we have the world annual energy consumption right here. For every year, on average, the world uses 5.3 times 10 to the 20th joules. And then we also have here, the other one that we're going to need for this problem, is how much water we're going to need for 6.9 times 10 to the 13th joules. That's going to be 1 liter of water for every 6.9 times 10 to the 13th joules. So we're going to come down here. We're going to start off with the joules or energy for the world per year. So that's 5.3 times 10 to the 20th joules per year. I want to change that to liters of water. And the table says for every 1 liter of water, it generates 6.9 times 10 to the 13th joules of energy. So I can cross off my joules, and that's left with liters of water per year, which is what we're looking for. So I'm going to put in my calculator 5.3 times 10 to the 20th over 1 times 1 over 6.9 times 10 to the 13th. And the calculator gives me 7.68 e to the 6th, which means 7.68 times 10 to the power of 6, and that was liters per water, and then that's per year. The next example that we're going to use for comparison is we're going to consider $100 billion. And one thing that I didn't put in this question, I'll make a note of it. We're going to talk about it in literally $1 bills. And so we want to compare it to how much time that it takes to count $100 billion to kind of imagine how big that would be. So if we imagine that it takes about 1 second to count each bill, we can start by saying it would take, for $100 billion, that would be 100 billion seconds because it's a second per dollar. And so 100 billion would be 100 times 10 to the 9th, because 10 to the 9th is billions, but that's not quite in scientific notation, because remember, scientific notation, this number in front needs to be a number between 1 and 10. So I'm going to rewrite this as 1 times 10 to the 11th, because I'm going to move it over 2 more places so I can write it in official scientific notation. So that's 1 times 10 to the 11th seconds. And now I want to change this into years, so I have an understanding of how long this is going to take to count in years. So I know that there are 60 seconds in 1 minute. There's 60 minutes in 1 hour. There are 24 hours in 1 day. And there's 365 days in 1 year. So now I've set it up so I can cross off my days, my hours, my minutes, and my seconds, and I'm left with how long in years this would take me to count, estimating that it would be about a second per dollar bill. So when I multiply that out on the calculator, I get 3.17 E3, which means 3.17 times 10 to the 3rd. If we write that in standard notation rather than scientific notation, that means I'm going to move my decimal place 3 places because I've got 10 to the 3rd. So I've got 3170 because this was where my decimal point is, or was. This was where my decimal point was, and I moved it over 3 places. So it's approximately 3,170 years it would take to count $100 billion. And keep in mind that we didn't calculate in any breaks, sleeping time, or anything like that. That would be straight through 3,170 years would be approximately how long it would take to count that amount of money. Okay, the next example, we're going to compare numbers by giving the factor by which the numbers differ. So we're going to just use division for that. So for example, if I said compare 8 and 4, you would say that 8 is bigger than 4 by a factor of 2 because 2 times 4 is 8, or you could look at it in reverse and use division and say 8 divided by 4 is 2. So that's all we're going to do here. We're going to use division, and so that we can compare the numbers to see by how much is one number bigger than the other. So when you first look at this, let's write out 250 million. Million means 6 zeros. So 1, 2, 3, 4, 5, 6. So there's 250 million. And then billion is 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to take 5,000, so we're going to take 5 billion, which is 5 times 10 to the 9th, because I've got 9 zeros. And then we're going to divide by 250 million, which would be 2.5 times 10 to the 8th, because I'm going to move my decimal place over 8 places. 1, 2, 3, 4, 5, 6, 7, 8 to get 2.5. Now when I divide that, I get 2 times 10 to the first, and 2 times 10 is just 20. So that means 5 billion is 20 times larger than 250 million. Okay, so looking at the second example, I want to compare 9.3 times 10 to the second and 3.1 times 10 to the negative 2. Since this has a negative exponent, this one's going to be smaller than the 9.3 times 10 to the second. So I'm going to take 9.3 times 10 to the second on top, and I'm going to divide by 3.1 times 10 to the negative 2. When I divide that, I get 30,000. So that means 9.3 times 10 to the second is 30,000 times bigger than 3.1 times 10 to the negative 2. All right, so far we've talked about perspective through estimations, perspective through comparisons. Now we're going to talk about perspective through scaling. And scales have many uses other than maps. So that's the first thing that comes to my mind, is looking at scales on maps. But there's other uses for that. Architects and engineers build scale models to visualize their plans. We have timelines that represents the scale of time. And we have time-lapse photography and computer simulations that allow us to represent large blocks of time in short periods. So the first example, we're going to talk about scaling on maps. It says 1 inch represents 1 mile on a map. What is the scale ratio for this map? So we want to compare inches on the map to what the actual inches are in real life. So 1 inch on the map is equal to 1 mile, 1 actual mile. And I know that 1 mile is equal to 5,280 feet. And I know that there are 12 inches in each foot. So now I can compare inches on the map to inches in real life, and actual inches. Okay, so I'm canceling off my feet, canceling off my miles, and what I'm left with is real inches compared to inches on the map, so we can compare them. So when I multiply this out, I'm going to take 1 over 1 times 1 over 5280 times 1 over 12. That's going to give me 1 inch on the map is equivalent to 63,360 inches in real life, in actual inches. So we could say that this is a 63360 to 1 scale. Okay, so now we're going to do an example of a scale model of the Earth and Sun system. And it says the distance from the Earth to the Sun is about 150 million kilometers. The diameter of the Sun is about 1.4 million kilometers. And the diameter of the Earth is about 12,760 kilometers. If you put these numbers into perspective by using a scale model, we're going to use the scale of 1 to 10 billion. Okay, so we have 3 things to check here. We have the distance from the Earth to the Sun. We have the diameter of the Sun. And then we have the diameter of the Earth that we want to scale. Okay, so the first thing we're going to scale is the distance from the Earth to the Sun. Okay, now it says the distance from the Earth to the Sun is actually 150 million kilometers, and millions means I'm going to add on 6 zeros. So 1, 2, 3, 4, 5, 6. And that's kilometers. And we want to do this on a scale from 1 to 10 billion. Now, billion is 9. So I'm going to take 10 and multiply by 10 to the 9th because it's 10 billion. Now we want to put this in actual scientific notation. It's got to be from 1 to 10, but less than 10. So I'm going to write this as 1, this should be equals, 1.5 times 10 to the 8th, because I'm going to move my decimal from here over 8 places. And then on the bottom, I'm going to write this as 1 times 10 to the 10, because I'm moving this over 1 place. So I'm going to add a number in my exponent from 9 to 10. Now, when I divide this on my calculator, I'm going to get 0.0015 kilometers. Now, that's really hard to imagine 0.0015 kilometers. So let's try to change it into meters. So I have 0.0015 kilometers. And I know that 1 kilometer is 1,000 meters. So if I multiply that out on my calculator, I'm going to get 15 meters. So that's a little bit easier to visualize, I think. So if we were making a scale model of the Earth and the Sun, we would put, and if it was on a scale of 1 to 10 billion, we would put the Earth and the Sun 15 meters apart, is what this is saying. Now for the second scale, we want to make a scale of the Sun's diameter. Now it says that the Sun's diameter is 1.4 million kilometers. And we want to do this on a scale of 1 to 10 billion. So like up here, we can just reuse what we did up here. We started off with 10 billion, so that's 10 times 10 to the 9th, because we add 9 zeros. But then we put it in actual scientific notation, and we rewrote it as 1 times 10 to the 10. So I'm just going to start from there, since we already did that work, and divide by 1 times 10 to the 10. I can put 1.4 million kilometers in scientific notation, and I can write that as 1.4 times 10 to the 6th kilometers, because we know that million means 6 zeros, and then that's divided by 1 times 10 to the 10. When I divide, I get 1.4 times 10 to the negative 4 kilometers. And again, that's a little bit hard to visualize. If I rewrite that in standard notation, that would be, let's see, 0.00014 kilometers, because I did have my decimal place here, and I moved it over 4 places, 1, 2, 3, 4. So 0.00014 kilometers is hard to imagine. So let's try putting it in meters. So I know 1 kilometer is equal to 1,000 meters. Okay, so when I multiply that out, I'm going to get 0.14 meters. That's still hard to imagine. I mean, it's a little bit easier than 0.0014 kilometers, but let's try changing it into centimeters now. 0.14 meters is equal to 14 centimeters. That's a little bit easier to visualize. So if we were making a scale model of the Earth and the Sun, so far we have it set up that the distance between them would be 15 meters, and the Sun's diameter would be 14 centimeters. So we would use some kind of a ball that would have a diameter of 14 centimeters. Okay, and the last thing that we need to scale is the Earth's diameter. Now it says the Earth's diameter is 1.276 times 10 to the 4th kilometers. And we want to divide by, again, since we're using the same scale for all of this, I'm just going to keep reusing the 1 times 10 to the 10. If the scale changes, that number is going to change. When I put that in on the calculator, I'm going to get 1.276 times 10 to the negative 6. That's equal to 0.0000001276, because I'm taking my decimal place and I'm moving it over 6 places. 1, 2, 3, 4, 5, 6, and that's in kilometers. So that's really hard to visualize something in kilometers that small. So let's try changing it into centimeters. We'll change it to meters and then into centimeters and see what we have. So we have 0.00001276 kilometers. I know that there's 1,000 meters in 1 kilometer. And I know that in 1 meter, there's 100 centimeters. When I do that, that's going to give me 0.1276 centimeters. That's still really hard to visualize. Let's try to change it then to millimeters. So 0.1276 centimeters is going to be equal to 1.276 millimeters. That's a little bit easier to comprehend. It's going to be really small. So if we were making an Earth-Sun scale, we would have the Earth and the Sun 15 meters apart. The Sun's diameter for the scale model, the ball would be about 14 centimeters wide in diameter. And then for the Earth, we would use a ball that was 1.276 millimeters wide in diameter. Okay, next example, it says, the distance from the Earth to the nearest stars beside the Sun, the 3 stars of Alpha Centauri system, is about 4.3 light years away. And we're going to use the same model scale. So on the 1 to 10 billion scale, how far are these stars from Earth? And we're going to note that a light year is the distance that a light can travel in 1 year, which is 9.5 times 10 to the 12th kilometers. So we want to figure out, using the 1 to 10 billion scale, how far the 4.3 light years away would be from the Earth. Okay, so we're going to start with 4.3 light years. And we said 1 light year is 9.5 times 10 to the 12th kilometers. 4.1 times 10 to the 13th kilometers. That's how far 4.3 light years away would be in kilometers. Now we want to take that 4.1 times 10 to the 13th kilometers and scale it on the 1 to 10 billion scale. So just like up above, I'm going to do 1 times 10 to the 10 for 1 billion. When I divide that, I have 4.1 times 10 to the 3rd kilometers. If I put that in standard notation, that is 4, and then I move my decimal place over 3 places, 1, 2, 3, so that's going to give me 4,100 kilometers. Other than making scale models or scales on maps, we could also use scaling to create a timeline, to get a sense of where we stand on a timeline. So in this example, it talks about human civilization, at least since the time of ancient Egypt, is on the order of 5,000 years old. The age of the Earth is 5 billion years. So the Earth has been around for 5 billion years. There's only been humans on Earth, for what we could tell, for about the last 5,000 years. And suppose we use the length of a football field, or about 100 meters, as a timeline to represent the age of the Earth. So if we imagine this is the length of a football field from 0 to 100 meters, approximately. And this is the age of the Earth from here to here. This is the timeline of how old Earth is. We want to figure out if we put the birth of Earth at the start of the timeline, so that would be this, the birth of Earth, and then this would be now. We want to see how far from the line's end would human civilization begin. So where on here, if I start making tick marks, where on here would humans appear? So what we're going to do is we're going to take 5,000 years out of the 5 billion years. Remember, billion is times 10 to the 9th, because that's 9 zeros. And we're going to figure out what that ratio is. If I put that on my calculator, I'm going to get 1 over 10 to the 6th. The calculator might give you 10 to the negative 6, or the calculator might give you 0.000001. Either way, it's a really small number. That would be 1 over 10 to the 6th, or 0.000001 of 100 meters. So what we're going to do is figure out what fraction of 100 meters that would be. So if I take 10 to the negative 6, or you can take the 0.000001, whichever you prefer, and multiply it by 100, that means it's going to be 0.0001 meters. So really, really close to the end, so that there's only 0.0001 meters from here to the end is going to be where human civilization started on this timeline. So we've studied several techniques for putting numbers into perspective, and sometimes we've had to use more than one technique, and sometimes we need additional creativity to think of ways to make sense of a particular number.